Okay, we observe the rotating strap. And from our observations, we come up with a graph of omega of t versus t, based on observations right after each new minute. Okay, so we get a series of about 6 points. And there's a slight curvature. I'm kind of maybe exaggerating the curvature a little bit, but there is a curvature to the graph. Okay, so that's a graph of what we call omega of t, angular velocity versus t, as sampled over intervals ranging from maybe 6 seconds to 10 or 12 seconds, with an uncertainty of 1 second in any given timing, so that these points won't all lie perfectly on the same smooth curve. Nevertheless, they lie very close, and we're able to make a pretty good curve. Okay, so there's our omega of t. So I'll label that omega versus t. Rotating strap. Sampled just after each minute. Now that's not really a good label, and that's too big for the title of a graph. So in any report that accompanies this graph, we want to explain some details, including details of our uncertainty. And we'll be working on that. So right here, maybe, is a good title, and this begins a description which would be written above, below, off to the side, whatever. Okay, there's the graph. Now, another observation that we can easily make is of theta versus t, the total angle of rotation. Okay, so this would be theta versus t and I'll abbreviate the explanation of what total rotations mean, or we put that off to the side, but it's total rotations. Okay? Now, when we do this graph, okay, our omega of t is in degrees per second. T is in seconds. Theta of t is going to be measured in rotations. When t is measured now in minutes. So measured in seconds, the rotating strap would go up to around 300 seconds. So let's just put a, excuse me, 300 here. And that should be visible. That wouldn't be visible on Zoom. Wouldn't be readable, but it should be readable if you're looking at this in full screen. If you got good eyes and good resolution on your phone, you can probably read it on your phone. Better read on a full screen, but as long as you can see everything, it's okay. Okay, well, theta of t is rotations versus minutes, and there are a total of about 5 minutes before the rotations end. So we can subdivide this graph, sort of. We could put 3 here and divide this into a couple of, okay, so that more or less evenly spaced markings here. And right now we're just doing hand-drawn graphs, so you want to do your best to evenly space your markings. So you can kind of follow some what I do. But now we have rotations. So let's just say that we have, I'm going to put 40 up here because it's easy to subdivide 40 and make a good graph. So I divide 40 into two parts. This one's a little high. I don't have real good perspective on this thing. I'm not straight across from it. So there are obvious inconsistencies. This mark is, the distance here is greater than the distance here, or the distance here, and they seem to be actually decreasing, which is going to distort my graph. So if I'm looking dead on this thing, if I can subdivide this accurately, I'll have a pretty good scale. Then we can plot the points. And I think the points that I gave you in class go something like this. And of course, we start out with 0 rotations, and your graph ends up looking something like this. Now, if you misread the instructions, which I think were clear, so you want to read carefully, the more I have to explain what I mean by what I've already said, the harder it gets to read the document. So when I write these documents, I've got to balance making the explanation so long you don't remember what the beginning of the last sentence was, and making it so short that everything's not clear. It has to be concise, and of course I won't always do the best possible job of that, but it has to be concise and clear. Okay. Okay, so anyhow, we've got these two graphs, and these graphs are rotated. Caught the word rotate out the corner of my eye, and it came right out of my mouth. Okay, these graphs are related. It was an R word. Okay, there are worse ones I could have probably come up with. These graphs aren't related. They're closely related. They don't have compatible units exactly. I mean, the units are compatible, but they're not identical. In other words, this is measured in seconds and degrees per second. So our unit of time is a second. Our unit of angular displacement is the degree. Down here, we're talking about minutes and rotations. And of course, it's not rotations per second, but we'll get to that in a minute. Now, rotations can easily be changed to degrees. Minutes can easily be changed to seconds. Matter of fact, since I mentioned it, I'm going to go ahead and do that. I'm going to relabel this graph, or give it a dual labeling. Here I've got 300, 60, 120, 180, 240. So now I can say this graph also expresses what happens in rotations versus seconds. And of course my rotations can be converted to degrees. They could be converted to radians. Multiply by 2 pi, you get the radians. Multiply by 360, you get the degrees. Now the numbers I get here are going to be kind of big. I'm going to get 3,600, 7,200, 10,800, 14,400. And those numbers are a little big, so I'm going to leave these numbers here and comment that the conversions can easily be made after we figure out various quantities on these graphs in the given systems of units. Since the systems of units are compatible, we have two recourses. We can relabel our axes, or we can do a conversion of units. And it's a simple conversion. as we'll see. Okay, now what we do, well, the first thing we do is we look at this graph and we say, okay, let's see. If I do what I call a fundamental triangle here, where I've got a run and a rise, the slope of that triangle is going to give me what? It's going to give me the change in theta divided by the change in t. So the slope is delta theta over delta t. Now, on the original board that I used in class, I'll move on to that. I'll talk more about details of this idea. Okay, so there's our slope. Now, as I commented, if I do this triangle, and okay, it's delta theta over delta t, but that is the change in the angle divided by the change in the time. And that's just an average angular velocity, as you'll know from what we did in class. So there's the slope. It's an average angular velocity. If I do slopes over smaller and smaller triangles, let me also comment, this average angular velocity is an approximation to the angular velocity at the midpoint of this interval over which I calculated the slope. Okay, so for an interval down here, there's a triangle up here. It has a slope, and that slope is a change in theta divided by a change in t, which is a number of degrees per second. Okay, change in number of degrees over the change in number of seconds gives us the degrees per second, which is kind of an intuitive idea of omega average, and it's actually a definition of omega average. And this is the approximate omega. And, I wonder if I'm recording here. Yeah, I am. I'd hate to get that far and realize I didn't have the thing recording. This is the approximate omega at the midpoint. I'll be more specific about this, but the midpoint of this interval. If you think about the rotations that occur between 2 minutes and 3 minutes, you count them, and if you want, convert that to degrees. So let's say you have 10 rotations in the second to the third minute. And that would be in the third minute, because between minute 0 and 1 is the first minute, between 1 and 2 is the second minute, between 2 and 3 is the third minute. So if you think about the rotations that occur in the third minute, it's probably more like 6 rotations or 5 or something like that. Okay? You know that it starts faster at the beginning of the minute. That corresponds up here. It's rotating faster, and more slowly at the end of the minute. Right in the middle is when the average angular velocity occurs, or approximately when the average angular velocity occurs. So the angular velocity at 3.5 minutes should be pretty close to this quantity. Now that should be something you think about until it's kind of intuitively obvious. You want to really understand that. Okay, now if we take these triangles and do approximations over shorter and shorter time intervals, we get tinier and tinier triangles. You can't even see that that's a triangle. I can't either, but I kind of tried to make it. So make these things tinier and tinier, that gives us omega average in tinier and tinier intervals. That approaches just plain old omega, not an omega average, because of course the midpoints of these tinier and tinier intervals approach, let's say the intervals run like this, and then the next interval is like this, and the next interval is just a little tiny interval like this. Okay, so a 1 minute time interval, maybe a 10-second time interval, maybe a 1 second time interval. Starting at 2 minutes, then the approximate omega at the midpoint is going to become the exact omega at 2 minutes. Okay, so let's see if I can fix this. Not very well, but okay, so I'm going to say that's an omega of t, and that's instantaneous. The instantaneous velocity at whatever time the interval starts. Let's say we start all these intervals at the same time, then we're shrinking down the calculation of the average velocity on the tinier intervals starting at that time. That approaches the instantaneous velocity. And that process should be something that you understood very well in your calculus course. Okay, well anyhow, there we have it. So there's an instantaneous angular velocity. Now, what's going to happen to these slopes as we approach this point? The slopes are going to approach the slope of the tangent line. Now, I had a question, you know, how do you estimate the tangent line? Do you just guess? What do you do? Well, to get the tangent line, take a straight edge. Actually, I got a meter stick here. You can use a piece of paper, but it's easier to make a mark with something a little more rigid. So the tangent line, as you should know very well, if you've even had a pre-calculus course, and everybody in here has had a calculus, it's going to be the line that touches this curve right at this one point. Okay? If I change the slope of this thing a little bit, it cuts through the curve. And I'm not going to go into detail what a tangent line is. I kind of assume everybody knows that. As I explained, whatever 2 points on this curve we use for an average angular velocity, we can estimate the coordinates if we don't know. And really your curve fits a bunch of data points that have fairly large uncertainties. You're not going to get a curve that actually goes through all your data points. Okay? Because the curve represents the actual behavior of the rotating strap. The data points are rational numbers. Whole number or a decimal number divided by another decimal number. Okay? And terminating decimal numbers. That's going to give you rational number approximations to the actual values of, in this case, theta, which can't possibly be equal to the irrational number that actually represents what the beam was doing. Okay, so whether you understand that or not, there are fluctuations in this data. You fit your curve as best you can to the data without actually trying to hit every data point. And then you take what you've got and you make estimates. So, for any 2 points in this curve that you want to use, even the data points, you base your estimates on the curve, not on your data points. Wherever the curve is, that's what you take. If the curve misses the data point, then the curve misses the data point. Well, okay, so we can make estimates. we can estimate the slope of the tangent line very easily. We simply take 2 points on the tangent line. Now you don't want the tangent line to be too short because of uncertainties in estimates. The shorter your tangent line is, the bigger any error in your estimate is going to factor into the calculation of the slope. So here I'm going to take a point. Let's pretend that's on the y-axis, just because that's convenient for this particular tangent line. Now we can project down here and project down here. We can say that, okay, this looks like 3.6. This, if I can keep it level, looks like it's maybe 32. And you can then construct a triangle here. Find its rise, find its run, find its slope. That slope is going to represent the instantaneous velocity that you get here. As you would do this over smaller and smaller triangles, the slope of the triangle approaches the slope of the tangent line. Again, something you should be very familiar with from calculus. Okay, so that's quite a bit about how you deal with these graphs. We want to go into more detail. Yeah, one more comment then. The angular velocity you get here from the tangent line should kind of closely match the angular velocity at the same time. Let's say this is at 2 minutes. Then here at 2 minutes, it should match the value of omega. So that omega from the tangent line occurs here. Omega from your data point is here. Actually, I'm going to kind of do this. I don't really have room to make this clear. Okay, this axis is a little bit above the curve. The curve actually came out a little below this data point for the reasons I was talking about before. You have the real behavior and you try to guess that as best you can. With the curve, you have your data point, which is not going to match the real behavior exactly. So you're going to have two other estimates of omega here, one from the curve and of course one from your data point. So you're going to get three different values of omega. We'll talk more in detail about that, but as an idea you want to kind of carry away. The omega from the tangent line will hopefully come fairly close to the omega that you get from the curve. Okay? Now one more comment, pushing it just a little further. The omega that you get if you do the fundamental triangle for the 2 to 3 minutes, in other words, the average velocity between 2 and 3 minutes should actually be, I'm just debating about what color to use, here, because the average velocity between 2 and 3 minutes occurs at 2.5 minutes. 2.5 minutes is 150 seconds. So this is it's small, it says omega average from a 1 minute interval. Okay, and that's actually worth a little bit more of a digression because there's a lot of insight about these graphs and what they're telling you before I go on to talk about what we did in class.